There is a moment, roughly twice each year, when Earth positions itself directly between our Sun and our Moon. In that alignment, something quietly remarkable happens. The bright face of the full moon begins to dim. Not suddenly, but gradually, as if someone was slowly turning down a cosmic dimmer switch. This is a lunar eclipse, and it represents one of the most accessible and peaceful astronomical events we can witness. You do not need special equipment to watch a lunar eclipse. Your eyes alone are sufficient. You do not need to travel to a specific location on Earth. If you happen to be on the night side of our planet when an eclipse occurs, you can simply step outside and look up. The moon will be there, slowly transforming before you, taking on colors that range from pale copper to deep burgundy, from brick red to sometimes almost complete darkness. The entire event unfolds over several hours, moving at the unhurried pace of celestial mechanics, following rules that have governed these patterns for billions of years. Understanding lunar eclipses means understanding shadows. Every object that blocks light creates a shadow, and Earth is no exception. As our planet orbits the Sun, it casts a long shadow into space, a shadow that extends far beyond the orbit of the Moon. Most of the time, the Moon passes above or below this shadow, traveling along its elliptical path around Earth without entering the darkness. But approximately twice each year, the geometry aligns. The Moon's orbital path intersects with Earth's shadow, and for a few hours, our natural satellite passes through that darkness. This is not a violent event. There are no sudden changes, no dangerous emissions, nothing that could harm anyone watching from Earth's surface. Instead, a lunar eclipse is a demonstration of geometry and light, of orbital mechanics operating with quiet precision. The Moon continues its journey around Earth at its usual speed of roughly 1,030 meters per second. Earth continues its rotation. The Sun continues to shine. But for a brief window of time, these three bodies align in such a way that Earth's shadow falls across the lunar surface. The Moon itself does not generate light. What we see when we look at the Moon is sunlight reflecting off its rocky surface. The lunar regolith, that layer of dust and broken rock covering the Moon's exterior, reflects a portion of the sunlight that strikes it. During a lunar eclipse, that direct sunlight is blocked by Earth. The Moon passes into our planet's shadow, and the reflected light diminishes. But here is something fascinating. Even during a total lunar eclipse, when the Moon is completely within Earth's darkest shadow, it does not disappear entirely. Instead, it glows with a reddish hue. This happens because Earth has an atmosphere, and that atmosphere bends some sunlight around the edges of our planet. The light that reaches the Moon during totality has passed through Earth's atmosphere, been filtered and refracted, and emerges as predominantly red and orange wavelengths. From the Moon's surface, looking back toward Earth during a total eclipse, an observer would see Earth as a dark disk surrounded by a brilliant ring of red light. All the sunrises and sunsets happening on Earth at that moment would combine to create that ring. The study of lunar eclipses reaches back thousands of years. Ancient astronomers in Babylon recorded lunar eclipses on clay tablets, noting the dates, the duration, and the degree of darkness. These observations, accumulated over centuries, allowed them to recognize patterns. They noticed that eclipses did not occur randomly, but followed predictable cycles. The most famous of these cycles is the Saros, a period of 18 years, 11 days, and 8 hours. After one Saros cycle, the geometry of the Sun, Earth, and Moon returns to nearly the same configuration, and a very similar eclipse occurs. This predictability meant that eclipses could be anticipated. Greek astronomers used this knowledge. Roman scholars recorded it. The ability to predict when the Moon would darken was both scientifically valuable and culturally significant. In some societies, eclipses were seen as omens. In others, they were simply phenomena to be studied and understood. The famous explorer Christopher Columbus used his knowledge of a predicted lunar eclipse in 1504 to convince the indigenous people of Jamaica that he had divine power, though historians note this story should be regarded with some skepticism. Today, we can predict lunar eclipses with extraordinary precision. Modern astronomical calculations can tell us not only the date and time of an eclipse, but exactly how it will look from any location on Earth. We can predict eclipses decades or even centuries in advance. The calculations involve tracking the Moon's complex orbit, which is influenced by the gravitational pull of both Earth and the Sun, as well as more subtle perturbations from other bodies in the solar system. The Moon's orbit is not a perfect circle. It is slightly elliptical, meaning the Moon's distance from Earth varies throughout each orbit. When the Moon is closest to Earth, at a point called perigee, it appears slightly larger in our sky. When it is farthest away, at apogee, it appears slightly smaller. This variation affects the appearance and duration of lunar eclipses. An eclipse that occurs when the Moon is at apogee, moving more slowly in its orbit, tends to last longer than one occurring when the Moon is at perigee. There is also the matter of orbital inclination. The Moon's orbit around Earth is tilted by approximately 5 degrees relative to Earth's orbit around the Sun. This tilt is the reason we do not see a lunar eclipse every single month. If the orbits were perfectly aligned, we would see a lunar eclipse at every full moon. But because of that 5-degree tilt, the Moon usually passes above or below Earth's shadow. Only when the full moon occurs near one of the 2 points where the Moon's orbital plane intersects Earth's orbital plane do we get an eclipse. These intersection points are called nodes, and they are critical to understanding eclipse patterns. As you listen to this, perhaps you are preparing for sleep or simply seeking a calm space in your day. The story of lunar eclipses is well suited to quiet contemplation. These are events that happen on a grand scale, involving bodies that are hundreds of thousands of kilometers apart. Yet we can observe them with nothing more than our own eyes and a clear sky. There is something deeply reassuring about the predictability of eclipses. They demonstrate that the universe operates according to understandable laws, that patterns exist on scales far larger than human concerns, and that we are part of a cosmic choreography that has been unfolding for billions of years. To understand lunar eclipses more deeply, we need to understand shadows. Not just the simple shadows we see on sunny days, but the complex structure of shadows cast by spherical bodies in space. When Earth blocks sunlight, it does not create a simple, sharply defined shadow. Instead, it creates a shadow with distinct regions, each with its own characteristics. The darkest part of Earth's shadow is called the umbra. This is the central core where the sun is completely blocked. If you were standing within Earth's umbra, looking back toward the sun, you would see the entire sun hidden behind Earth. No direct sunlight reaches this region. The umbra is cone-shaped, extending from Earth into space, gradually narrowing as it extends farther from our planet. At the Moon's distance from Earth, which averages about 384,400 kilometers, the width of Earth's umbra is approximately 9,200 kilometers. This is considerably larger than the Moon's diameter of 3,474 kilometers, which means the Moon can easily fit entirely within the umbra during a total eclipse. Surrounding the umbra is the penumbra, a region of partial shadow. Within the penumbra, only part of the sun is blocked by Earth. If you were standing within the penumbral zone, you would see part of the sun's disk peeking around Earth's edge. The farther you move from the umbra toward the outer edge of the penumbra, the more of the sun becomes visible. The penumbra is much wider than the umbra, gradually fading from near darkness at the umbra's edge to full sunlight at its outer boundary. This two-part shadow structure determines what type of lunar eclipse will occur. When the Moon passes through only the penumbra, we have a penumbral lunar eclipse. These are subtle events. The Moon dims slightly, but the change is so gradual and minimal that many observers do not even notice an eclipse is occurring. Only careful observers with experience can detect the slight shading across the lunar surface during a penumbral eclipse. When the Moon enters the umbra, even partially, the eclipse becomes much more dramatic. This is a partial lunar eclipse, where a dark, curved shadow begins to creep across the Moon's bright surface. The edge of the umbra is fairly well defined, creating a noticeable boundary between the bright portion of the Moon, still in sunlight, and the darkened portion within Earth's shadow. As more of the moon enters the umbra, the curved shadow advances across the lunar disk, taking on the distinctive curved shape of Earth's shadow. If the moon passes completely into the umbra, we have a total lunar eclipse. This is when the entire moon is within Earth's darkest shadow. No direct sunlight reaches the lunar surface, yet the moon does not disappear. It takes on that characteristic reddish color, glowing with light that has been filtered through Earth's atmosphere. The exact shade varies from one eclipse to another depending on conditions in our atmosphere at the time. The umbra extends far into space. At Earth's surface, we are only about 12,742 kilometers from Earth's center, but Earth's umbral shadow extends approximately 1,384,000 kilometers into space on average. This means the shadow reaches more than 3 times farther than the moon's average distance from Earth. The moon, in its orbit, passes through only a small fraction of the total length of Earth's shadow. The shape of the umbra is determined by the geometry of the Sun and Earth. The Sun is much larger than Earth, with a diameter of approximately 1,390,000 kilometers compared to Earth's diameter of about 12,742 kilometers. Because the Sun is so much larger, Earth's shadow tapers as it extends into space, eventually coming to a point. This tapering is why the umbra narrows with distance from Earth. Within the umbra, the level of darkness is not perfectly uniform. The deepest part of the umbra is along its central axis, the line extending directly away from the Sun through Earth's center. The closer you move toward the edge of the umbra, the closer you are to the penumbra, and the less dark the shadow becomes. This variation in darkness affects how a lunar eclipse appears. During totality, the part of the moon closest to the center of the umbra appears darker than the parts near the umbra's edge. The penumbra tells a different story. It is a gradual transition zone. At its inner edge, bordering the umbra, almost all of the Sun is blocked. At its outer edge, almost none of the Sun is blocked. Between these extremes is a continuous gradient. The penumbra is much less studied in popular eclipse discussions because it is visually subtle, yet it is essential to understanding the full structure of an eclipse. Every total or partial lunar eclipse begins and ends with a penumbral phase. The moon first enters the penumbra, experiences a gradual dimming, then enters the umbra for the more dramatic portion of the eclipse. As the moon exits, it reverses this sequence, leaving the umbra, crossing through the penumbra, and finally returning to full sunlight. The penumbra is roughly twice as wide as the umbra at the moon's distance from Earth. While the umbra has a width of about 9,200 kilometers, the penumbra extends for approximately 16,000 kilometers in total width. This means that if the moon's orbit just barely misses the umbra, the moon can still pass through a significant portion of the penumbra, creating a penumbral eclipse that, while subtle, is still technically an eclipse event. One fascinating aspect of Earth's shadow is that it is always present. Right now, as you listen to this, Earth is casting its shadow into space. The umbra and penumbra extend continuously away from our planet on the opposite side from the Sun. Most of the time, the moon is nowhere near this shadow, passing above it or below it during its monthly journey around Earth. But twice a year, on average, the moon's path brings it into that shadow, and we witness an eclipse. The stability of Earth's shadow over human timescales is remarkable. The basic geometry has remained essentially unchanged throughout all of recorded human history. Ancient Babylonians saw the same umbral shape creep across the moon that we see today. The mathematics describing these shadows was worked out centuries ago, and those same equations still accurately predict modern eclipses. This constancy reflects the underlying stability of the solar system over periods of thousands of years. The orbits may shift very slightly over geological time, but within the span of human civilization, the patterns remain essentially constant. Understanding these shadows helps us appreciate the precision involved in eclipse prediction. Astronomers must calculate the exact position of the moon in its orbit, the exact size and shape of Earth's shadow at that point in space, and the timing of when these positions coincide. They must account for the moon's varying speed at different points in its elliptical orbit, the slight wobbles in Earth's orientation, and even small irregularities in the moon's motion caused by gravitational interactions with other bodies. Yet despite all this complexity, predictions are accurate to within seconds. Lunar eclipses are classified into three main types, each defined by which part of Earth's shadow the moon encounters. These classifications are not arbitrary. They reflect fundamental differences in the eclipse experience and what observers on Earth will see. A penumbral lunar eclipse occurs when the moon passes through only the penumbral portion of Earth's shadow, never entering the darker umbra. From a purely technical standpoint, this is an eclipse. The moon is within Earth's shadow, and sunlight reaching, the moon is partially blocked. However, the visual effect is minimal. An observer watching the moon during a penumbral eclipse might notice a very slight dimming, a subtle shading across one side of the lunar disk. In many cases, observers do not realize an eclipse is happening at all unless they have been informed in advance and are watching carefully. Penumbral eclipses are common. Over the 5,000-year period from 2000 BCE to 3000 CE, approximately 36.3% of all lunar eclipses are penumbral. This means that more than one-third of lunar eclipses produce only this subtle effect. Among penumbral eclipses, most are partial penumbral eclipses, where only part of the moon enters the penumbra. A small fraction, about 1.2% of all lunar eclipses, are total penumbral eclipses. During these rare events, the entire moon passes through the penumbra while just barely avoiding the umbra. These are slightly more noticeable than partial penumbral eclipses, and sharp-eyed observers can detect a definite shading across the entire lunar surface, but they still lack the dramatic appearance of umbral eclipses. A partial lunar eclipse occurs when part of the moon enters Earth's umbra. This is where eclipses begin to look truly dramatic. A dark, curved shadow appears on the moon, advancing across the bright lunar surface. The edge of this shadow is fairly distinct, creating a clear boundary between the shadowed region and the sunlit portion. As the eclipse progresses, the shadow gradually covers more of the moon. At maximum eclipse, some fraction of the moon is darkened by the umbra, while the remainder stays brightly lit. The portion of the moon within the umbra appears much darker than the portion still in sunlight. This creates a striking visual contrast. Ancient observers noted that the shadow has a curved edge, and this observation provided one of the early proofs that Earth is round. The fact that Earth's shadow on the moon always appears curved, regardless of when the eclipse occurs, indicates that Earth must be spherical. A flat Earth would cast differently shaped shadows depending on its orientation. Partial eclipses can range from just barely partial, where only a tiny edge of the moon dips into the umbra, to nearly total, where almost the entire moon is darkened except for a small crescent still in sunlight. The magnitude of a partial eclipse is measured by what fraction of the moon's diameter enters the umbra. An eclipse with a magnitude of 0.5 means half of the moon's diameter is within the umbra at maximum eclipse. An eclipse with a magnitude of 0.9 means 90% of the moon's diameter is darkened. Over the 5,000-year period previously mentioned, approximately 34.9% of lunar eclipses are partial. This means partial and penumbral eclipses together account for more than 70% of all lunar eclipses. The remaining roughly 28.8% are total eclipses. A total lunar eclipse occurs when the entire moon passes completely into Earth's umbra. This is the most spectacular type of lunar eclipse. As totality begins, the last bright edge of the moon slides into the umbra, and the entire lunar disk takes on that characteristic reddish glow. The moon does not disappear. Instead, it transforms, becoming a dull, coppery sphere hanging in the sky. The appearance during totality varies considerably from one eclipse to another. Some total eclipses produce a bright, orange-red moon that remains easily visible. Other eclipses result in a much darker moon, sometimes appearing deep brownish-red or even nearly invisible at mid-totality. This variation depends primarily on conditions in Earth's atmosphere at the time of the eclipse. If Earth's atmosphere is relatively clear, more light is refracted around the planet to illuminate the moon, resulting in a brighter total eclipse. If the atmosphere contains significant amounts of dust or volcanic ash, more light is blocked, resulting in a darker eclipse. There is a scale for rating the darkness of total lunar eclipses called the Danjon scale, named after French astronomer André Danjon, who devised it. The scale ranges from L equals 0 to L equals 4. An L equals 0 eclipse is very dark, with the moon almost invisible, especially at mid-totality. An L equals 1 eclipse is dark, gray or brownish in color, with details on the lunar surface distinguishable only with difficulty. An L equals 2 eclipse produces a deep red or rust-colored moon with a very dark central shadow but a relatively bright outer edge. An L equals 3 eclipse is brick red with the umbral shadow usually having a bright or yellow rim. An L equals 4 eclipse is very bright, copper red or orange, with an umbral shadow that appears bluish and has a very bright rim. Major volcanic eruptions can significantly affect the appearance of total lunar eclipses. When a volcano ejects large amounts of ash and sulfur dioxide into the stratosphere, this material can remain suspended for months or even years. During this time, any total lunar eclipses that occur tend to be much darker because the volcanic particles block more of the light that would normally be refracted around Earth to illuminate the moon. The total lunar eclipse of December 1992, which occurred shortly after the eruption of Mount Pinatubo in the Philippines, rendered the moon nearly invisible during totality. This dramatic darkening demonstrated how sensitive lunar eclipses are to atmospheric conditions. Every total lunar eclipse is also, technically, a partial eclipse and a penumbral eclipse, because the moon must pass through these outer shadow zones to reach totality. The sequence is always the same. First, the moon enters the penumbra. This marks the beginning of the penumbral phase, though it is usually not visible to casual observers. Then the moon enters the umbra, marking the beginning of the partial phase. A dark shadow begins to creep across the lunar surface. This partial phase continues as more and more of the moon enters the umbra. Finally, when the entire moon is within the umbra, totality begins. After totality ends, the sequence reverses. The moon gradually exits the umbra during another partial phase, then exits the penumbra, returning to its normal brightness. The duration of each phase varies depending on the eclipse geometry. If the moon passes through the center of the umbra, the eclipse tends to last longer and the partial phases are more symmetric. If the moon passes through the edge of the umbra, the eclipse is shorter and the geometry is less symmetric. In some cases, the moon just barely achieves totality, with the entire disk spending only a few minutes fully within the umbra before beginning to exit. In other cases, totality can last well over an hour. The classification of a lunar eclipse depends entirely on the geometry at the moment of maximum eclipse. Maximum eclipse is defined as the moment when the moon is closest to the center of Earth's shadow. At this moment, the greatest amount of the moon is within the shadow. If even a tiny sliver of the moon remains outside the umbra at maximum eclipse, the eclipse is classified as partial, not total. Only when 100% of the moon is within the umbra at maximum eclipse is the event classified as total. There is a special category within total lunar eclipses called central lunar eclipses. These occur when the moon passes near or through the center of Earth's umbra, specifically passing close to the anti-solar point. During a central lunar eclipse, the moon follows a path that takes it deep into the umbra, resulting in a particularly long and often particularly dark totality. About 59.6% of all total lunar eclipses are central. Understanding these three types helps frame expectations for eclipse viewing. If you learn that a penumbral eclipse is approaching, you know not to expect dramatic visual changes. If a partial eclipse is coming, you can anticipate a gradual darkening of part of the moon over the course of an hour or more. If a total eclipse is predicted, you can plan to observe the entire sequence, from the initial dimming through the spectacular totality and the gradual return to full brightness. The most visually striking aspect of a total lunar eclipse is the color. Instead of disappearing into blackness when Earth's shadow covers it, the moon glows red. This phenomenon has led to the popular term blood moon, though this name is more recent and somewhat sensationalized compared to the straightforward term total lunar eclipse used by astronomers. The red color is not intrinsic to lunar eclipses. It is not caused by anything on the moon itself. Rather, it is entirely due to Earth's atmosphere. To understand why this happens, we need to understand how. Light interacts with small particles. Sunlight appears white to our eyes, but it is actually composed of all the colors of the visible spectrum, from violet through blue, green, yellow, orange, and red. Each color corresponds to light of a specific wavelength. Violet light has the shortest wavelength, around 380 nanometers. Red light has the longest wavelength, around 700 nanometers. When light encounters particles that are smaller than its wavelength, something interesting happens. The light scatters. This scattering is not random. Shorter wavelengths scatter much more strongly than longer wavelengths. This phenomenon is called Rayleigh scattering, named after the 19th century British physicist Lord Rayleigh, who worked out the mathematics. Rayleigh scattering is inversely proportional to the fourth power of the wavelength. This means that blue light, with its short wavelength, scatters about 5.9 times more strongly than red light. This is why Earth's sky appears blue. Sunlight entering our atmosphere encounters molecules of nitrogen and oxygen, which are much smaller than the wavelength of light. The blue wavelengths scatter in all directions, filling the sky with blue light. The longer wavelengths, particularly red and orange, pass through the atmosphere more directly. During a lunar eclipse, something similar happens, but the geometry is different. Light from the sun approaches Earth. Most of it either strikes Earth's surface or is blocked entirely by Earth's mass. But a small amount of sunlight passes through Earth's atmosphere at the planet's edge, specifically through the atmosphere at the day-night terminator, the boundary between day and night on Earth. This is the atmosphere experiencing sunrise and sunset. As sunlight passes through this atmospheric ring, it travels through a long path of air. Along this path, the shorter wavelengths, the blues and violets, scatter away. They bounce off air molecules and particles spreading out in many directions, and most of them never make it through. The longer wavelengths, the reds and oranges, are scattered less. They pass through the atmosphere more successfully. Additionally, Earth's atmosphere acts as a lens, refracting or bending this light. The combination of refraction and selective scattering means that red and orange light gets bent around Earth's edge and directed into the umbra, where it can reach the moon. From the moon's perspective during a total eclipse, Earth appears as a dark disk blocking the sun. But around the edges of that dark disk is a brilliant ring of reddish light. This ring is the combined light of all the sunrises and sunsets happening on Earth at that moment. Imagine every place on Earth where the sun is rising or setting. All of that light, filtered through atmosphere and turned predominantly red and orange, combines to create the ring that illuminates the moon during totality. The exact color the moon displays during totality depends on several factors. The primary factor is the clarity of Earth's atmosphere. If the atmosphere is relatively clean and clear, more light makes it through, and the moon appears brighter and more orange. If the atmosphere contains significant dust or other particles, less light gets through, and the moon appears darker and redder, possibly even brownish. Volcanic eruptions have a dramatic effect on eclipse colors. When a major volcanic eruption occurs, it can inject enormous quantities of sulfur dioxide and ash particles into the stratosphere. The sulfur dioxide converts to sulfate aerosols, tiny particles that remain suspended in the stratosphere for months or years. These particles are very effective at scattering and absorbing light. During the period following a major eruption, total lunar eclipses tend to be much darker. The 1980 eruption of Mount St. Helens, the 1991 eruption of Mount Pinatubo, and other major volcanic events have all left their mark on the appearance of subsequent lunar eclipses. Forest fires and dust storms can also affect eclipse colors, though usually to a lesser degree than volcanic eruptions. Any event that increases the amount of particulate matter in Earth's atmosphere can darken an eclipse. Conversely, periods with unusually clear atmospheric conditions can produce brighter eclipses. There is another subtle effect that some experienced eclipse observers have reported. At the very beginning and end of totality, when the moon is just barely fully within the umbra, some observers have detected a pale blue or turquoise band along the moon's edge. This blue color is thought to be caused by light passing through Earth's ozone layer. Ozone absorbs red light but allows blue light through, creating a brief moment when blue light can reach the moon's edge before the main body of red filtered light dominates. The specific shade of red or orange observed during any given eclipse depends on which part of Earth's atmosphere the light passes through. If the eclipse occurs when Earth's atmosphere along the terminator has a lot of clear air, the color will be brighter and more orange. If that atmospheric ring includes areas with significant cloud cover, dust, or volcanic ash, the eclipse will be darker. The brightness of the eclipsed moon is also affected by its path through the umbra. If the moon passes through the center of the umbra, it is deeper within the shadow and receives less refracted light, appearing darker. If the moon passes through the edge of the umbra, it is closer to the penumbra and receives more light, appearing brighter. Additionally, the part of the moon closest to the center of the umbra always appears darker than the parts near the edge. From Earth's surface, the red moon during totality presents a striking sight. It is clearly visible as a disk, distinctly red or orange, dimmer than the full moon but bright enough to see details. The Maria, the dark. Volcanic plains on the moon's surface can often still be distinguished from the lighter highland regions, though the contrast is reduced. Stars that would normally be invisible near the full moon become visible, because the eclipsed moon is so much dimmer than normal. The red color during totality is a powerful reminder of Earth's atmosphere. Without our atmosphere, the moon would simply disappear during a total eclipse, becoming invisible in the darkness of the umbra. The fact that we can see the moon at all during totality is direct evidence of our atmosphere's presence and its effect on light. Ancient observers did not understand this mechanism, but they certainly noticed the red color and incorporated it into their eclipse observations. The term blood moon gained widespread popularity in the early 21st century, particularly in 2013 and 2014 in connection with a tetrad of total lunar eclipses. Some religious groups interpreted these eclipses as having prophetic significance. From an astronomical standpoint, the term simply describes the appearance of the moon during totality. Every total lunar eclipse is, in this sense, a blood moon. The moon turns red not through any supernatural mechanism, but through the well-understood physics of light scattering in Earth's atmosphere. The moon does not orbit Earth in the same plane that Earth orbits the sun. If it did, we would see a lunar eclipse at every full moon and a solar eclipse at every new moon. Instead, the moon's orbit is tilted. This tilt is approximately 5.1 degrees relative to Earth's orbital plane around the sun. This seemingly small angle has profound consequences for when eclipses can occur. Earth's orbital plane around the sun is called the ecliptic. The ecliptic is the reference plane for the solar system. When astronomers describe the positions of planets, moons, and other objects, they often describe them in terms of ecliptic coordinates. The moon's orbital plane intersects the ecliptic at 2 points. These intersection points are called nodes. The point where the moon crosses the ecliptic from south to north is called the ascending node. The point where the moon crosses from north to south is called the descending node. The moon crosses through the nodes twice during each orbit around Earth. Since the moon completes one orbit roughly every 27.3 days, it crosses a node about every 13.7 days. But for an eclipse to occur, the moon must be at or very near a node at the same time it is either full or new. This requirement drastically reduces the frequency of eclipses. The period from one node crossing back to the same node is called the Draconic month. The name comes from ancient mythology, where the nodes were associated with a celestial dragon. The ascending node was called the dragon's head, and the descending node was called the dragon's tail. The term draconic persists in modern astronomy. One draconic month is approximately 27.21222 days. Because the draconic month is shorter than the synodic month, the period from one full moon to the next, about 29.53 days, the nodes slowly drift relative to the moon's phases. Over time, this drift means that sometimes a full moon occurs near a node, enabling a lunar eclipse, and sometimes it occurs far from the nodes, making an eclipse impossible. For a lunar eclipse to occur, the full moon must occur when the sun is within approximately 18.5 degrees of a node. This creates a window of time, called an eclipse season, during which eclipses are possible. An eclipse season lasts between 31 and 37 days, with an average of about 34 days. During an eclipse season, if a full moon occurs, there will be at least a penumbral lunar eclipse. If the full moon occurs close enough to the node, there will be a partial or total lunar eclipse. Eclipse seasons occur twice per year. They are separated by approximately 173 days. This interval is roughly half an eclipse year, which is the time it takes for the sun to return to the same node. One eclipse year is about 346.62 days, shorter than a calendar year by about 18.64 days. This means that eclipse seasons occur about 19 days earlier each year. Between eclipse seasons, eclipses cannot occur. The moon continues to go through its phases, reaching full moon once per month, but if the full moon occurs when the moon is far from the nodes, the moon passes above or below Earth's shadow and no eclipse takes place. This is the normal situation. Most full moons do not produce eclipses because the geometry is not aligned. The nodes themselves are not stationary. They slowly move along the ecliptic, drifting westward at a rate of approximately 19.35 degrees per year. This movement, called nodal precession or regression of the nodes, means that the nodes complete one full revolution around the ecliptic every 18.6 years. This precession is caused by the gravitational influence of the Sun on the Moon's orbit. The inclination of the Moon's orbit is also not constant. It oscillates slightly, varying between about 5.00 degrees and 5.30 degrees. The inclination is greatest when the Sun is aligned with the nodes, and smallest when the Sun is 90 degrees away from the nodes. This variation affects the detailed geometry of eclipses, but does not change the fundamental pattern of eclipse seasons. Within a single eclipse season, it is possible to have multiple eclipses. A typical eclipse season will contain one lunar eclipse and one solar eclipse, occurring about 2 weeks apart. Sometimes, if the first eclipse occurs early in the eclipse season, there is time for a third eclipse before the season ends. The maximum number of eclipses in one calendar year is 7, though this is rare. More commonly, there are 4 or 5 eclipses per year. The fact that eclipse seasons occur roughly every 6 months means that lunar eclipses come in pairs, separated by approximately 6 months. If there is a total lunar eclipse in March, there is likely to be another eclipse in September. The 2 eclipses in a pair occur at opposite nodes. One occurs when the moon crosses the ascending node, and the other occurs when the moon crosses the descending node. The spacing of eclipse seasons is not perfectly regular. Because the synodic month and the draconic month are not exact multiples of each other, the timing of when full moons occur relative to the nodes varies. Sometimes a full moon occurs very close to a node, producing a deep total eclipse. Sometimes it occurs farther from a node, producing a shallow total eclipse or a partial eclipse. Sometimes it occurs just barely within the eclipse limit, producing a penumbral eclipse that is barely noticeable. The moon's elliptical orbit adds another layer of complexity. When the moon is near perigee, its closest approach to Earth, it appears larger and moves faster. When it is near apogee, its farthest point from Earth, it appears smaller and moves slower. This variation affects eclipse durations. An eclipse occurring when the moon is at apogee and moving slowly tends to last longer. An eclipse occurring when the moon is at perigee and moving quickly tends to be shorter. The combination of the draconic month, the synodic month, the anomalistic month, the period from perigee to perigee, and the precession of the nodes creates a complex pattern of eclipses. Ancient astronomers, particularly the Babylonians, kept meticulous records of eclipses over many years. By comparing these records, they gradually uncovered patterns. They noticed that eclipses tend to repeat with a period of about 18 years. This discovery led to the identification of the Saros cycle, which we will explore in detail in the next section. Understanding eclipse seasons and the moon's orbital geometry helps explain why eclipses are both predictable and relatively infrequent. They are predictable because the orbital mechanics follow precise mathematical laws. They are infrequent because the required alignment of the moon's phase and the moon's position relative to the nodes occurs only a few times per year. This combination makes each eclipse a noteworthy event, yet ensures that careful observers can witness multiple eclipses during a human lifetime. Among the many cycles and patterns in astronomy, few are as elegant and historically significant as the Saros cycle. The Saros is a period of approximately 6,585.32 days, equivalent to 18 years, 11 days, and 8 hours. After one Saros cycle, the geometry of the Sun, Earth, and Moon returns to nearly the same configuration, and an eclipse very similar to the previous one occurs. The discovery of the Saros cycle is attributed to ancient Babylonian astronomers, who kept detailed records of celestial events on clay tablets. These records extended over centuries, allowing Babylonian scholars to compare eclipses separated by long intervals. Sometime around the 7th or 8th century BCE, they recognized that eclipses repeat with this 18-year pattern. The regularity was striking enough that they could use it to predict future eclipses with reasonable accuracy. The name Saros itself has an interesting history. It derives from a Babylonian term Sa, meaning 3,600 years. However, this original meaning had nothing to do with eclipses. The current usage of Saros to describe the eclipse cycle was popularized by the English astronomer Edmund Halley in 1691. Halley was studying a Byzantine lexicon when he encountered a reference to the Babylonian eclipse period of 223 months. He applied the word Saros to this period, even though the connection to the original Babylonian term was somewhat confused. Despite this historical mix-up, the name stuck, and astronomers have used Saros to describe the 18-year eclipse cycle ever since. The reason the Saros works is mathematical. 3 different lunar orbital periods happen to be almost exactly equal in duration when multiplied by appropriate integers. One Saros period equals 223 synodic months, full moon to full moon, which is 6,585.3223 days. It also equals 239 anomalistic months, perigee to perigee, which is 6,585.5375 days, and it equals 242 draconic months, node to node, which is 6,585.3575 days. These 3 periods are nearly identical, differing by only a few hours. This near-perfect alignment means that after one Saros, the moon returns to nearly the same phase, nearly the same distance from Earth, and nearly the same position relative to the nodes. Because these 3 conditions largely determine what type of eclipse will occur and how it will appear, eclipses separated by one Saros are remarkably similar. However, the Saros is not perfect. The 8-hour difference between one Saros and an integer number of days has an important consequence. Earth rotates once every 24 hours, so 8 hours corresponds to 1/3 of a rotation, or 120 degrees of longitude. This means that after one Saros, the eclipse occurs 120 degrees westward on Earth's surface compared to the previous eclipse. If one eclipse is visible from North America, the next eclipse in the same Saros series will be visible primarily from the Pacific Ocean and Eastern Asia, and the eclipse after that will be visible from Europe and Africa. Every 3 Saros periods, which equals 54 years and 34 days, the eclipses return to roughly the same longitude on Earth. This longer cycle, called the exiligmos, was also known to ancient astronomers. After one exiligmos, an eclipse will be visible from nearly the same region of Earth as the original eclipse. Eclipses are organized into Saros series. Each series begins when an eclipse occurs at one of the nodes with the moon, far enough from the node that the eclipse is just barely visible as a small penumbral eclipse. Over the course of many Saros cycles, the moon's position at each subsequent eclipse gradually shifts. The eclipses in the series become deeper and more central. Eventually, the series produces partial eclipses, then total eclipses. After reaching maximum centrality, the eclipses gradually become less central, eventually returning to partial eclipses, then penumbral eclipses, and finally, the series ends. A typical lunar eclipse Saros series lasts between 1200 and 1500 years and contains between 69 and 87 eclipses. The variation depends on the specific geometry and the rate at which the moon's position shifts within each cycle. For lunar eclipses, there are currently dozens of active Saros series, each producing an eclipse every 18 years. The Saros series are numbered. For solar eclipses, the numbering system was established in the 19th century and continues today. For lunar eclipses, a similar numbering system exists. Odd-numbered series begin at the ascending node, while even-numbered series begin at the descending node. By tracking which Saros series an eclipse belongs to, astronomers can understand its place in the larger pattern of eclipses. The gradual shift in the moon's position within each Saros series is caused by the fact that the three periods, synodic, anomalistic, and draconic months, are not exactly equal. The small differences accumulate over time. Additionally, the sun's position relative to the nodes shifts slightly with each Saros because one Saros is not exactly equal to an integer number of years. For lunar eclipses, the shift in the moon's position within each Saros series typically moves the eclipse northward or southward through Earth's shadow, depending on whether the series is at the ascending or descending node. This shift means that early eclipses in a series pass through the southern or northern edge of the shadow, while later eclipses pass through the central regions. The series ends when the eclipses shift far enough that the moon misses Earth's shadow entirely. The existence of the Saros demonstrates that the seemingly complex motions of the sun, Earth, and moon contain hidden regularities. Ancient astronomers, without modern computers or even telescopes, were able to recognize these patterns through careful observation and record-keeping over many generations. This achievement speaks to both the dedication of ancient scholars and the mathematical elegance of celestial mechanics. Modern astronomers still use the Saros cycle, not because they need it to predict eclipses. Computers can calculate eclipses far more precisely, but because it provides a useful way to organize and categorize eclipses. By knowing which Saros series an eclipse belongs to, astronomers can quickly understand that eclipse's relationship to past and future eclipses. The Saros also played a role in history beyond astronomy. The ability to predict eclipses gave ancient astronomers and priests significant prestige and influence. In some societies, correctly predicting an eclipse was seen as evidence of divine favor or supernatural power. Even today, people sometimes use eclipse predictions to demonstrate the reliability of scientific knowledge, though our modern understanding goes far beyond simply recognizing patterns. A lunar eclipse unfolds over several hours, passing through distinct phases as the moon enters and exits Earth's shadow. Understanding these phases helps observers know what to expect and when to watch most carefully. Unlike a solar eclipse, which is visible only from a small portion of Earth's surface and lasts only minutes, a lunar eclipse is visible from the entire night side of Earth and proceeds at a leisurely pace. The entire sequence of a total lunar eclipse typically spans about 3.5 to 4 hours from the moment the moon first touches the penumbra until it completely exits. The specific duration depends on the eclipse geometry, particularly how centrally the moon passes through the umbra. The eclipse begins when the moon's leading edge enters the penumbra. This moment is called P1, or first contact. At this point, a slight dimming may begin on one edge of the moon, though it is usually too subtle for casual observers to notice. The moon continues moving through the penumbra for roughly an hour before reaching the next phase. Second contact, called U1, occurs when the moon's edge first touches the umbra. This is when the eclipse becomes visually obvious to observers. A dark, curved shadow appears on the moon's eastern limb. The eastern limb is the edge of the moon that leads in its orbit. The shadow is noticeably darker than the penumbral shading and has a relatively sharp edge. From this point, the partial phase has begun. During the partial phase, the dark umbral shadow gradually advances across the moon's face. The process takes about an hour. The bright remaining portion of the moon contrasts sharply with the darkening portion in shadow. As the shadow advances, more and more lunar features disappear into darkness. The maria and craters on the moon's surface are swallowed by Earth's shadow in sequence. The third contact, U2, marks the beginning of totality. This occurs when the moon is completely within the umbra. The last bright edge of the moon slips into shadow, and the moon transforms from partly shadowed to fully shadowed. The change at this moment can be dramatic. Just before totality, the remaining bright crescent of the moon can make the rest of the lunar disk appear quite dark by contrast. Once that bright edge disappears, the entire moon becomes visible again, now glowing with its characteristic red or orange color. Totality is the phase that most observers find most compelling. The moon's appearance during totality depends on the factors discussed earlier: atmospheric conditions, path through the umbra, and presence of volcanic ash or dust. The duration of totality varies significantly between eclipses. It depends primarily on how centrally the moon passes through the umbra and on the moon's orbital speed at that time. The moon's average orbital speed is approximately 1,030 meters per second, or about 2,300 miles per hour. At this speed, the moon travels roughly its own diameter, 3,474 kilometers, in just over 1 hour. This speed determines how long it takes the moon to traverse the umbra. The maximum possible duration of totality is approximately 107 minutes, or 1 hour and 47 minutes. This theoretical maximum would occur under ideal conditions when the moon passes exactly through the center of the umbra. The moon is at apogee, moving at its slowest, and Earth is at perihelion, closest to the sun, making Earth's shadow as large as possible. In practice, few eclipses approach this maximum duration. The longest total lunar eclipse of the 20th century occurred on July 26, 1953. Its totality lasted 100 minutes and 43 seconds. The longest total lunar eclipse of the 21st century occurred on July 27, 2018. Its totality lasted 1 hour, 42 minutes, and 57 seconds. This eclipse achieved such long duration because the moon passed nearly through the center of the umbra and was close to apogee. At the other extreme, some total lunar eclipses have very brief totalities. If the moon just barely becomes fully engulfed in the umbra, totality might last only a few minutes or even seconds. The shortest total lunar eclipse of the 21st century occurred on April 4, 2015. Its totality lasted only 4 minutes and 43 seconds. Despite its brevity, it was still officially a total eclipse because the entire moon was within the umbra, even if only just barely. The moment of greatest eclipse occurs at the midpoint of totality. This is when the moon is closest to the center of Earth's shadow. At this moment, the moon appears its darkest, particularly if passing near the shadow's center. The brightness distribution across the moon during totality is not uniform. The portion of the moon closest to the shadow's center appears darker than the portions near the umbra's edge. After greatest eclipse, the moon begins to emerge from the umbra. Fourth contact, U3, marks the end of totality. One edge of the moon exits the umbra, and a bright crescent begins to appear. This signals the start of the second partial phase. The bright crescent grows as more of the moon emerges from the umbra. This partial phase is essentially a reversal of the first partial phase, lasting about an hour. Fifth contact, U4, occurs when the moon completely exits the umbra. At this point, the entire moon is once again outside the darkest part of Earth's shadow, though still within the penumbra. The moon appears almost back to normal, with only a slight dimming on one side due to the penumbral shadow. The eclipse ends at sixth contact, P4, when the moon completely exits the penumbra. The moon now appears as a normal full moon, with no trace of the shadow that engulfed it over the previous several hours. Observers on Earth do not need special equipment to watch any phase of a lunar eclipse. Unlike solar eclipses, which require eye protection, lunar eclipses are completely safe to observe with the naked eye. Binoculars or a small telescope can enhance the view, making it easier to see details on the lunar surface and to appreciate subtle color variations during totality, but they are not necessary. The duration of the entire event, from P1 to P4, can be up to about 3 hours and 45 minutes for an eclipse with long totality, or as short as about 3 hours and 20 minutes for an eclipse with brief totality. This extended duration means that observers can watch the eclipse unfold without feeling rushed. The pace is contemplative, matching the scale of celestial mechanics. One interesting phenomenon that can occur during a total lunar eclipse is called a Selene lion or horizontal eclipse. This happens when both the sun and the eclipsed moon are visible above the horizon at the same time. This might seem impossible since a lunar eclipse requires the sun and moon to be on opposite sides of Earth. However, atmospheric refraction bends the light from both the sun and moon, making them appear slightly higher in the sky than their true geometric positions. If an observer is at just the right location, on a mountain or elevated plain, when the eclipse occurs at sunrise or sunset, they may see both the sun rising in the east and the eclipsed moon setting in the west simultaneously. This experience is more about the observer's experience than a separate type of eclipse, but it adds to the sense of wonder that eclipses can inspire. Among the various patterns in lunar eclipses, one of the most interesting is the tetrad. A tetrad is a series of 4 consecutive total lunar eclipses, each separated by approximately 6 months, with no partial or penumbral eclipses in between. These 4 total eclipses occur over a span of about 18 to 24 months, creating an unusual concentration of total lunar eclipses in a short period. Tetrads are not extremely rare, but they are not common either. Their frequency varies significantly, depending on the era. During some centuries, several tetrads occur. During other centuries, none occur at all. This variation is related to the eccentricity of Earth's orbit and the timing of eclipse seasons. The mechanism that produces tetrads involves the relationship between the synodic month and the spacing of eclipse seasons. Eclipse seasons occur roughly every 6 months, or more precisely, every 173 days. A synodic month is about 29.5 days. If the timing is just right, a full moon can occur near a node during 4 consecutive eclipse seasons, and if the geometry is favorable each time, all 4 of these eclipses can be total rather than partial or penumbral. This requires a specific set of conditions. The full moons must occur close enough to the nodes to produce total eclipses, but not so close to the center of the shadow that the sequence is interrupted by differing geometries. Additionally, the moon's distance from Earth during each eclipse must be within a range that allows totality to occur. During the 300-year period from 1600 to 1900, no tetrads occurred at all. This was a period when the orbital geometry did not favor the production of tetrads. Then, beginning in the early 20th century, tetrads began to occur again. There were tetrads in 1900, 9 to 1910, 1927 to 1928, 1949 to 1950, 1967 to 1968, 1985 to 1986, and 2003 to 2004. The most recent tetrad occurred in 2014 to 2015. The 4 eclipses of this tetrad were visible from various parts of the world, with at least part of each eclipse visible from North America. The dates were April 15, 2014, October 8, 2014, April 4, 2015, and September 28, 2015. This tetrad received significant public attention, partly due to the term blood moon being popularized during this period. The term blood moon in the context of tetrads has religious and cultural dimensions that go beyond astronomy. Some Christian pastors and authors suggested that the 2014 to 2015 tetrad had prophetic significance, tying it to interpretations of biblical passages that mention the moon turning to blood. From a purely astronomical perspective, the eclipses of this tetrad were interesting but not fundamentally different from other total lunar eclipses. The moon turned red during totality for the same reason it always does during total eclipses, Rayleigh scattering in Earth's atmosphere. The current century, the 21st century, will see 8 tetrads. After the 2014 to 2015 tetrad, the next tetrads will occur in 2032 to 2033, 2043 to 2044, 2050 to 2051, 2061 to 2062, 2072 to 2073, and 2090 to 2091. The frequency of tetrads is related to the eccentricity of Earth's orbit. When Earth's orbit is more circular, the conditions that allow 4 consecutive total lunar eclipses are less common. When Earth's orbit is more elliptical, tetrads occur more frequently. Over very long time scales, spanning thousands of years, the frequency oscillates. During some millennia, tetrads are abundant. During others, they are absent entirely. The 300-year gap between 1700 and 2000, when no tetrads occurred, was not unusual from a long-term astronomical perspective. Similar gaps have occurred in the past and will occur again in the future. The current era, from the early 20th century through the 22nd century, represents a period when conditions favor tetrad formation. By the 23rd and 24th centuries, tetrads will become less common again. Each eclipse within a tetrad belongs to the same Saros series. The 4 eclipses that make up a tetrad are not randomly selected eclipses that happen to be total and consecutive. Rather, they represent a specific geometric configuration where the moon's path through the umbra is similar for each of the 4 eclipses, with the geometry slowly evolving but remaining within the range that produces totality. From an observational standpoint, watching all 4 eclipses of a tetrad offers an opportunity to see how subtle variations in the eclipse, geometry, and atmospheric conditions affect the moon's appearance during totality. Each of the 4 eclipses will have a slightly different color and brightness, depending on the path through the umbra and the state of Earth's atmosphere at the time. Some tetrads have shown dramatic variations between the 4 eclipses, while others have been remarkably consistent. The 2014 to 2015 tetrad was notable partly because all 4 eclipses were visible from at least part of North America, making it particularly accessible to observers in that region. This was somewhat unusual. For many tetrads, the 4 eclipses are spread across different parts of Earth's surface due to the Saros shift of 120 degrees longitude between eclipses. The fact that North American observers could see multiple eclipses from the same tetrad contributed to the public interest during that period. Lunar eclipses have been witnessed by every human culture that has looked at the night sky. Long before the development of modern astronomy, people watched the moon transform during eclipses and tried to understand what they were seeing. The interpretations varied widely, shaped by each culture's mythology, religion, and understanding of the natural world. In ancient Mesopotamia, particularly among the Babylonians, lunar eclipses held significant importance. The Babylonians were careful observers of the sky. They recorded eclipses on clay tablets, noting the date, duration, and appearance. These records extended over many centuries. The earliest known eclipse records from Babylon date back to approximately the 8th century BCE, though the astronomical tradition there likely extends even further into the past. For the Babylonians, eclipses were not merely astronomical curiosities. They were viewed as omens, particularly concerning the welfare of the king. The belief was that an eclipse could presage the death of the king or other significant events affecting the kingdom. To protect the actual king, The Babylonians developed an elaborate ritual called the substitute king ceremony. When an eclipse was predicted, they would install a temporary substitute king who would symbolically bear any ill effects of the eclipse. The real king would step aside temporarily, and after the eclipse passed, the substitute would be removed, sometimes fatally, and the real king would resume his position. This practice demonstrates both the sophistication of Babylonian eclipse prediction and the cultural weight they placed on these events. They had discovered the Saros cycle, which allowed them to predict when eclipses were likely to occur. Yet, despite this predictive capability, or perhaps because of it, they maintained the interpretation of eclipses as messages from the gods. The ancient Chinese also kept detailed astronomical records, including eclipse observations. One of the earliest recorded lunar eclipse observations in China dates to 1136 BCE, documented in historical texts. Chinese astronomers developed their own methods for predicting eclipses. By approximately the 3rd century CE, Chinese astronomers could predict both lunar and solar eclipses with reasonable accuracy. In Chinese mythology, eclipses were explained as a celestial dragon or dog eating the sun or moon. During an eclipse, people would bang drums, pots, and pans to frighten away the creature and rescue the celestial body. This tradition of making noise during eclipses was not unique to China. Similar practices existed in many cultures around the world, suggesting a common human response to the unsettling sight of a celestial body disappearing. In ancient Greece, lunar eclipses contributed to scientific understanding. The Greek philosopher Aristotle, who lived from 384 to 322 BCE, used lunar eclipses as one of his proofs that Earth is spherical. He noted that Earth's shadow on the moon during a lunar eclipse is always circular, regardless of when the eclipse occurs or how high the moon is in the sky. This observation led him to conclude that Earth must be round, since only a spherical body casts a circular shadow from all orientations. Greek astronomers also used lunar eclipses for more practical purposes. By observing the same eclipse from different locations and noting the local time at each location, they could determine the longitude difference between those locations. This technique, though challenging to execute with ancient technology, demonstrated an understanding of how eclipses could be used as tools for geographical measurement. The Greek astronomer Hipparchus, who lived in the 2nd century BCE, used Babylonian eclipse records to improve astronomical calculations. He recognized that the Babylonian observations, accumulated over centuries, provided valuable data for understanding the moon's motion. This cross-cultural exchange of astronomical knowledge represents an early example of international scientific collaboration. Roman historians occasionally mention lunar eclipses in their accounts of historical events. The historian Tacitus recorded a lunar eclipse that occurred in 14 CE, shortly after the death of the Roman Emperor Augustus. According to Tacitus, Roman soldiers stationed along the Rhine frontier saw the eclipse and interpreted it as an omen. The eclipse occurred near the beginning of the night, and by the time it reached totality, the soldiers had become agitated, viewing the darkened moon as a sign of divine displeasure. In Hindu tradition, lunar eclipses are associated with the demon Rahu. According to Hindu mythology, Rahu was once a demon who disguised himself to drink the nectar of immortality during a cosmic churning of the ocean. The sun and moon recognized the deception and alerted the gods, who beheaded Rahu. However, because Rahu had already consumed some of the nectar, his head became immortal. As revenge, Rahu periodically swallows the sun or moon, causing eclipses. Because Rahu is only a head without a body, the sun or moon passes through and reappears. This mythological explanation persists in Hindu culture, and even today some practitioners observe specific rituals during eclipses. It is customary for some Hindus to fast for several hours before an eclipse and to bathe after it concludes. Food prepared before the eclipse is often discarded, as it is considered spiritually affected. These practices reflect the enduring cultural significance of eclipses, even in an era when their astronomical nature is well understood. Among the Maya civilization of Mesoamerica, eclipses were carefully observed and recorded. The Dresden Codex, a Mayan manuscript dating to approximately the 11th or 12th century CE, contains detailed astronomical tables, including tables for predicting eclipse possibilities. The Maya developed a sophisticated understanding of eclipse cycles, though their approach was based on pattern recognition from observations rather than a physical model of orbital mechanics. The Maya associated eclipses with specific deities and believed they held divinatory significance. Different types of eclipses were thought to portend different outcomes. The careful recording of eclipses in the codices suggests that Mayan priests used this information for both religious and political purposes, much as the Babylonians did. In Islamic astronomy, which flourished from the 8th through the 15th centuries, lunar eclipses were studied as natural phenomena. Islamic scholars translated and expanded upon Greek astronomical texts, and they made their own observations of eclipses. The astronomer al-Battani, who lived from approximately 858 to 929 CE, made precise observations of lunar eclipses and used them to refine calculations of the moon's orbit. One notable historical incident involving a lunar eclipse occurred on January 27, 632 CE, which coincided with the death of Ibrahim, the son of the Prophet Muhammad. Some people interpreted the eclipse as a supernatural sign related to Ibrahim's death. According to Islamic tradition, Muhammad addressed this interpretation directly, explaining that eclipses are natural events that occur according to the will of God, but that they are not caused by the death or birth of any person. This teaching reinforced an understanding of eclipses as astronomical phenomena rather than omens tied to specific earthly events. In European medieval and Renaissance periods, lunar eclipses continued to be viewed with a mixture of scientific interest and superstitious dread. Christopher Columbus famously used his knowledge of a predicted lunar eclipse during his fourth voyage to the Americas. In 1504, Columbus and his crew were stranded in Jamaica, and relations with the indigenous inhabitants had deteriorated. Columbus knew from astronomical tables that a lunar eclipse would occur on February 29, 1504. He told the indigenous leaders that his god would show displeasure by darkening the moon. When the eclipse occurred as he predicted, the indigenous people, according to Columbus's account, were frightened and restored their support to Columbus and his men. This story, while often retold, should be understood with some caution. It comes primarily from Columbus's own account, and historians note that it portrays the indigenous people as superstitious and easily manipulated, which may not accurately reflect their actual understanding or response. Nonetheless, the story illustrates how astronomical knowledge could be used as a tool of power and how eclipses retained cultural and psychological significance even among those who understood their astronomical nature. By the 17th and 18th centuries, lunar eclipses had become important tools for scientific research. Astronomers used eclipse observations to refine their understanding of the moon's orbit and to test theories of gravitation. The timing of eclipses could be predicted with increasing precision, and discrepancies between predictions and observations led to improvements in orbital theory. In the modern era, lunar eclipses continue to fascinate both scientists and the general public. They are no longer viewed as omens or supernatural events by the scientific community, but they retain their ability to inspire wonder. The accessibility of lunar eclipses, visible to anyone on the night side of Earth without special equipment, means that millions of people can share the experience of watching the moon transform. This shared experience connects modern observers to all the humans throughout history who have watched lunar eclipses and wondered at the mechanics behind them. In the 21st century, our ability to predict lunar eclipses has reached extraordinary precision. Modern calculations, aided by computers and refined models of orbital mechanics, can predict the timing of an eclipse to within seconds, decades, or even centuries in advance. This predictive capability is the culmination of centuries of astronomical observation and mathematical refinement. The foundation of modern eclipse prediction is our understanding of the moon's orbit. The moon's motion around Earth, while governed by relatively simple physical laws, exhibits complex behavior due to various gravitational influences. The primary force acting on the moon is Earth's gravity, but the Sun also exerts a significant gravitational pull on the Moon. Additionally, the Moon experiences smaller perturbations from other bodies in the solar system, primarily Jupiter and Venus. These gravitational influences cause the Moon's orbit to be more complex than a simple ellipse. The orbital parameters, such as the size, shape, and orientation of the orbit, as well as the position of the nodes, all vary over time. Calculating the Moon's precise position at any given moment requires accounting for all these variations. The mathematical framework for this calculation was developed over centuries. Isaac Newton's law of universal gravitation, published in 1687, provided the theoretical foundation. Newton showed that the same force that causes an apple to fall to the ground also governs the motion of celestial bodies. Applying this law to the Moon's orbit, however, proved challenging. The three-body problem, calculating the motion of the Moon under the influence of both Earth and the Sun, does not have a simple closed-form solution. Over the 18th and 19th centuries, mathematicians and astronomers developed increasingly sophisticated approximation methods. Leonhard Euler, Joseph Louis Lagrange, Pierre-Simon Laplace, and others made significant contributions to lunar theory. They derived series of mathematical terms, each representing a specific periodic variation in the Moon's motion. By including enough terms in these series, they could predict the Moon's position with remarkable accuracy. In the 20th century, electronic computers revolutionized eclipse prediction. What previously required months of tedious hand calculation could now be done in seconds. Modern ephemerides, tables of celestial body positions, are calculated using numerical integration of the equations of motion. These calculations account for the gravitational effects of all major bodies in the solar system and incorporate relativistic corrections based on Einstein's general theory of relativity. The Jet Propulsion Laboratory's development ephemerides, particularly DE431 and its successors, represent the current state of the art. These ephemerides are used by space agencies worldwide for spacecraft navigation and by astronomers for precise predictions of celestial events. The positions given in these ephemerides are accurate to within meters over periods of decades. For lunar eclipses, the predictions must account not only for the positions of the Sun, Earth, and Moon, but also for the size and shape of Earth's shadow. The shadow calculation is more complex than it might first appear. Earth is not a perfect sphere. It is slightly flattened at the poles, a shape called an oblate spheroid. This flattening affects the shape of the shadow. Additionally, Earth's atmosphere refracts light around the planet's edge, effectively enlarging the shadow. Modern eclipse predictions include corrections for both Earth's oblateness and atmospheric refraction. The duration of an eclipse and the exact timing of the various contacts depend on the Moon's speed at the time of the eclipse. The Moon's speed varies because its orbit is elliptical. When the Moon is at perigee, about 363,000 kilometers from Earth, it moves at approximately 1,082 meters per second. When it is at apogee, about 405,500 kilometers from Earth, it moves at about 964 meters per second. This variation in speed directly affects how long the Moon takes to traverse Earth's shadow. The 21st century will witness 228 lunar eclipses. Of these, 86 will be penumbral, 57 will be partial, and 85 will be total. This distribution is typical. Over long periods, roughly 1/3 of lunar eclipses are penumbral, 1/3 are partial, and slightly less than 1/3 are total. The frequency of lunar eclipses varies from year to year. The minimum number of lunar eclipses in a calendar year is 0, though this is rare. More commonly, there are 2 or 3 lunar eclipses per year. The maximum number is 5, though this is also uncommon. In the 21st century, 4 eclipses occur in the years 2009, 2020, 2038, 2056, 2085, and 2096. For any given location on Earth, the frequency of visible eclipses is lower than the global frequency. This is because lunar eclipses are only visible from the night side of Earth. An observer remaining at one location and assuming clear skies might see roughly half of all lunar eclipses. Over an 18-year period, the span of one Saros cycle, an observer at a single location might see 19 or 20 lunar eclipses of all types, including penumbral, partial, and total. The visibility of a particular eclipse depends on whether the observer is on the night side of Earth when the eclipse occurs. The eclipse itself, from first contact to last contact, typically lasts 3 to 4 hours. The moon rises and sets over the course of a day as Earth rotates, so observers in some regions will see the entire eclipse. Observers in others will see only part of it, seeing either moonrise or moonset during the eclipse, and observers in still other regions will miss it entirely because the moon is below their horizon. Unlike solar eclipses, lunar eclipses do not require any special viewing precautions. Looking at a lunar eclipse is completely safe for the eyes. This is because the moon, even when fully illuminated by sunlight, is dim enough that it does not harm the eyes. During an eclipse, when the moon is darkened, it is even dimmer. Observers can watch a lunar eclipse with their naked eyes, with binoculars, or with a telescope, all with complete safety. This accessibility is one reason why lunar eclipses are beloved by amateur astronomers and the general public. The predictability of lunar eclipses makes them ideal for public outreach and education. Astronomy organizations, planetariums, and observatories often host eclipse viewing events. These events bring together people of all ages and backgrounds to witness a celestial phenomenon. The slow pace of a lunar eclipse makes it suitable for educational explanation. As the moon slowly enters the penumbra, then the umbra, then achieves totality, educators have time to explain each phase and answer questions from the audience. In the modern era, eclipses also serve scientific purposes. While the basic mechanics of lunar eclipses are well understood, they still provide opportunities for research. For example, measuring the exact brightness and color of the moon during totality provides information about Earth's atmosphere. The amount of dust, volcanic ash, and other particles in the stratosphere affects how much light is refracted around Earth to reach the moon. By comparing eclipse observations with atmospheric measurements, scientists can better understand how particles in the upper atmosphere affect light transmission. Lunar eclipses have also been used to study the moon's thermal properties. When the moon is in Earth's shadow, it cools rapidly because it is no longer receiving direct sunlight. The rate of cooling depends on the thermal properties of the lunar surface material. By measuring the infrared radiation from the moon during an eclipse, scientists can infer properties of the regolith, the layer of dust and broken rock covering the moon's surface. As we move further into the 21st century, eclipses will continue to be events that blend science, education, and cultural experience. They remind us that we live on a planet that is part of a larger cosmic system, that the motions of celestial bodies follow predictable patterns, and that humans have developed the knowledge to understand and predict these patterns with remarkable precision. As we near the end of this journey through the nature of lunar eclipses, it is worth pausing to reflect on what these events represent. A lunar eclipse is an alignment, a moment when three celestial bodies, the Sun, Earth, and Moon, fall into a specific geometric arrangement that has repeated countless times over billions of years and will continue to repeat for billions of years to come, barring any catastrophic changes to the solar system. The Moon orbits Earth at an average distance of about 384,400 kilometers. This distance is not constant. It varies by about 50,000 kilometers over the course of each orbit. The Moon is also slowly moving away from Earth, receding at a rate of about 3.8 centimeters per year. This recession is caused by tidal interactions between Earth and the Moon. The same tidal forces that cause our ocean tides also transfer rotational energy from Earth to the Moon's orbital motion, gradually pushing the Moon farther away. Billions of years ago, when the Moon first formed, it was much closer to Earth, perhaps only 30,000 kilometers away. At that distance, the Moon would have appeared enormous in Earth's sky, more than 10 times larger than it does today. Earth's day was also much shorter, perhaps only 5 hours long, because Earth rotated faster. Over geological time, tidal interactions have gradually slowed Earth's rotation and pushed the moon farther away. This process continues today, though at a very slow rate. The gradual recession of the moon has implications for eclipses. As the moon moves farther from Earth, its apparent size in our sky decreases. Currently, the moon's apparent size is very close to the sun's apparent size. This near equality is what makes total solar eclipses so spectacular, allowing the moon to just barely cover the sun's disk. In the distant future, as the moon recedes, it will appear smaller than the sun, and total solar eclipses will no longer occur. However, lunar eclipses will continue to happen, largely unchanged, because they depend on Earth's shadow rather than the apparent sizes of celestial bodies. The timescale for these changes is vast. The changes in Earth's rotation and the moon's orbit occur over millions of years. Within the span of human history, even recorded human history spanning several thousand years, the changes are imperceptible. The lunar eclipses observed by ancient Babylonians were essentially identical to the lunar eclipses we observe today. The eclipses that will occur 1,000 years from now will also be essentially identical. This constancy is reassuring. It demonstrates that the universe operates according to stable, understandable laws. The mathematical equations that Newton and others developed to describe celestial mechanics are not just approximations or convenient fictions. They genuinely describe how the universe works. The fact that we can predict eclipses centuries into the future with high accuracy is a testament to both the regularity of nature and the power of human understanding. Lunar eclipses also remind us of our place in the solar system. Earth is a planet orbiting the sun. The moon is a natural satellite orbiting Earth. These motions are not abstract concepts, but real physical phenomena that we can observe. When we watch a lunar eclipse, we are watching Earth's shadow, our planet's shadow, cast across another world. The reddish glow of the eclipsed moon is light that has passed through Earth's atmosphere. It is our atmosphere, filtering and bending sunlight, that illuminates the moon during totality. This connection to our planet is profound. The air we breathe, the atmosphere that shields us from harmful solar radiation, the atmosphere that creates our weather and sustains life, is the same atmosphere that turns the moon red during an eclipse. The eclipse becomes a kind of mirror, showing us Earth's presence and influence extending into space. The regular occurrence of eclipses also illustrates the concept of cycles and patterns in nature. The Saros cycle, with its 18-year period, demonstrates that complex astronomical phenomena can be reduced to understandable patterns. Ancient astronomers, without computers or even basic calculating tools, recognized these patterns through patient observation over many lifetimes. This achievement speaks to human curiosity and persistence. Eclipses are events that connect us to the past and to the future. Every human civilization that has looked at the sky has seen lunar eclipses. Ancient farmers watching from Mesopotamian fields, Greek philosophers debating in Athenian academies, Mayan priests recording observations in bark paper books, medieval monks noting eclipses in monastery chronicles, and modern observers watching from city rooftops or rural fields all have shared the experience of seeing the moon darken and turn red. Each observer brought their own understanding and interpretation. For some, eclipses were omens to be feared or rituals to be performed. For others, they were puzzles to be solved or tools for measurement. Today, we understand the mechanics behind eclipses, but this understanding does not diminish the experience. Instead, it enriches it. Knowing that the red color comes from Rayleigh scattering in our atmosphere does not make the sight less beautiful. Understanding the orbital mechanics that produce the Saros cycle does not make the pattern less elegant. As you listen to this, perhaps in the quiet of evening or the stillness of night, consider that the patterns being described are playing out right now. The moon is moving in its orbit. Earth is rotating. The nodes are slowly precessing. All the mechanisms that produce eclipses are continuously operating, whether we observe them or not. The next eclipse season is approaching, and when the geometry aligns, there will be another eclipse, continuing an unbroken sequence that extends back to the formation of the Moon over 4 billion years ago. The scientific understanding of eclipses does not remove them from the realm of human experience. Rather, it connects us more deeply to the physical universe we inhabit. We are not separate from these celestial mechanics. We are part of them. Earth, our home, is one of the bodies participating in this dance. Our very existence is possible because of the stable patterns that govern the solar system, patterns that allow life to develop and persist over billions of years. Watching a lunar eclipse can be a meditative experience. The slow progression of the shadow across the Moon unfolds at a pace that encourages patience and sustained attention. Unlike many modern experiences, which are fast-paced and demand quick responses, an eclipse invites us to slow down, to watch, to simply be present as the universe demonstrates its workings. The darkness that falls during totality is not absolute. Stars become visible that were previously hidden by the Moon's brightness. The landscape takes on a different quality. If you are fortunate enough to be in a dark location away from city lights during a total lunar eclipse, you may notice that the night becomes deeper, richer. The Milky Way, if it is above the horizon, becomes more prominent. You become more aware of the night sky as a three-dimensional space, with the eclipsed Moon as a distinctly reddish object against the black backdrop studded with countless stars. This awareness of depth and distance is another gift that eclipses offer. The Moon is not a flat disk painted on the sky. It is a spherical world, 3,474 kilometers in diameter, covered with mountains, valleys, and vast plains of solidified lava. The Sun is not a simple light source, but a massive sphere of incandescent plasma, 1.4 million kilometers in diameter, 93 million miles away. Earth's shadow, which we cannot see directly, but whose effects we observe on the Moon, is a three-dimensional cone extending over 1 million kilometers into space. These vast scales are difficult to comprehend in everyday experience, but eclipses make them tangible. The geometry becomes visible. You can see the curved edge of Earth's shadow creeping across the Moon. You can see the progression from penumbra to umbra to totality. You can watch as the Moon emerges, as the shadow retreats, as normal brightness is restored. All of this happens at a pace determined by the Moon's orbital speed and the size of Earth's shadow, quantities that can be measured and calculated. The predictability and regularity of eclipses also offer a form of comfort. In a world where many things seem uncertain or chaotic, the motions of celestial bodies remain steady. The Sun will rise tomorrow. The Moon will go through its phases. Eclipse seasons will occur at their appointed times. This predictability is not guaranteed by any human effort. It simply is. It exists because of the fundamental laws of physics, laws that operated long before humans existed and will continue to operate long after we are gone. Yet our ability to understand these laws is itself remarkable. Through observation, thought, and calculation, humans have decoded the patterns of the cosmos. We have built models that accurately describe the motions of planets and moons. We have created mathematical frameworks that allow us to predict future eclipses and reconstruct past ones. This intellectual achievement is one of the great accomplishments of our species. As the next eclipse approaches, whenever that may be, consider taking the time to observe it. Find a location with a clear view of the Moon. Allow yourself the unhurried hours needed to watch the entire sequence from beginning to end. Bring a blanket or a chair for comfort, perhaps some warm beverages if the night is cool. Invite others to join you, or go alone if you prefer solitude. Watch as the Moon enters the penumbra. Wait for the umbral shadow to appear. Observe the progression toward totality. Notice the color during totality. See how it changes across the Moon's disk. Watch the emergence, the reversal of the sequence you witnessed at the beginning. And as the Moon returns to its full brightness, reflect on what you have seen. You have witnessed the shadow of your own planet cast across another world. You have seen light that has traveled through Earth's atmosphere and illuminated the Moon from 150 million kilometers away. You have been part of a pattern that connects you to every human who has ever watched an eclipse and to every human who will watch eclipses in the future. This is the gift that lunar eclipses offer, a connection to the cosmos, to history, to the future, and to the fundamental nature of the universe in which we live. The Moon continues its orbit. Earth continues its rotation. The Sun continues to shine. These motions, governed by gravitation and inertia, proceed with or without our observation. Yet when we do observe, when we take the time to watch a lunar eclipse unfold over the course of several hours, we participate in something larger than ourselves. We engage with the mechanics of the solar system in a direct, visceral way. Lunar eclipses are remarkable in their accessibility. They require no special equipment, no travel to specific locations, no complex preparations. If you happen to be on the night side of Earth when an eclipse occurs, you simply step outside and look up. The moon will be there, transformed. This simplicity is part of their enduring appeal. In an era of increasingly complex technology, where astronomical observations often involve elaborate instruments and specialized knowledge, lunar eclipses remain something that anyone can experience. The pace of a lunar eclipse matches the scale of astronomical events. The universe operates on timescales that range from the nearly instantaneous, such as the flight of photons, to the unimaginably slow, such as the evolution of galaxies. Lunar eclipses fall at a human-friendly point on this spectrum. They last long enough to be observed and appreciated without requiring an investment of days or weeks, yet they proceed slowly enough that there is no need to rush, no fear of missing a critical moment in the blink of an eye. As this exploration of lunar eclipses comes to a close, I want to thank you for listening. Whether you have listened to the entire presentation in one sitting or have returned to it multiple times, your attention and interest are appreciated. The topics covered here, from the basic geometry of Earth's shadow to the ancient Saros cycle, from the colors produced by atmospheric scattering to the patterns of tetrads, represent just a fraction of what can be learned about lunar eclipses. Each topic could be expanded, each detail could be explored further. Astronomy is a field of endless depth, where even seemingly simple phenomena reveal layers of complexity and beauty upon closer examination. If this presentation has sparked your interest in lunar eclipses, I encourage you to seek out opportunities to observe one yourself. Check astronomical calendars for upcoming eclipse dates. Plan ahead, particularly for total lunar eclipses, which are the most spectacular. Find a viewing location with a clear view of the moon and minimal light pollution if possible. Bring patience and a sense of wonder. Watch the entire event if you can. Notice how the moon's appearance changes at each phase. Think about the geometry that produces what you are seeing. Remember that the reddish glow is sunlight filtered through Earth's atmosphere. Consider that you are seeing Earth's shadow, your planet's shadow, cast across another world. You might also consider learning more about related topics. The moon itself, with its complex surface features, its history of formation, and its continuing influence on Earth through tides, is a fascinating subject. Solar eclipses, the counterpart to lunar eclipses, offer their own unique experiences and challenges. The broader field of orbital mechanics, which governs not just eclipses but the motions of all celestial bodies, provides insights into how the universe works at its most fundamental level. Astronomy has a remarkable ability to put our everyday concerns into perspective. When you look at the moon and realize it is 384,000 kilometers away, when you think about the sunlight that has traveled 150 million kilometers from the sun to Earth and then been bent around Earth to reach the moon during an eclipse, when you consider that these patterns have been repeating for billions of years, your immediate worries may seem less overwhelming. This shift in perspective is not an escape from reality, but rather a deeper engagement with reality at its largest scales. The story of lunar eclipses is also a story of human curiosity and achievement. From ancient Babylonian astronomers recording eclipses on clay tablets, to Greek philosophers using eclipses to prove Earth is round, to modern scientists using eclipses to study Earth's atmosphere, humans have continually found new ways to learn from these events. This tradition of observation, questioning, and understanding continues today. Each new generation brings fresh eyes and new tools to the study of the cosmos. If you have found this journey through the nature of lunar eclipses to be interesting or relaxing, please consider liking this video and subscribing to Nebula Nights. Subscribing allows you to be notified when new content is available, and likes help this content reach others who might enjoy it. The goal of Nebula Nights is to provide detailed, accurate, and calming explorations of astronomical topics. There are many more subjects to explore, from the nature of other celestial events to the properties of distant objects in our solar system and beyond. Your support through likes and subscriptions makes it possible to continue creating this content. Thank you again for your time and attention. May your next view of the moon, whether during an eclipse or on an ordinary night, bring you a sense of connection to the vast universe in which we all live. May you find peace in the regular rhythms of celestial mechanics, and may the knowledge that these patterns are predictable and understandable bring you a sense of calm. The moon will continue its orbit. Earth will continue its journey around the sun. And occasionally, the geometry will align, Earth's shadow will fall across the moon, and those of us on Earth's night side will have the opportunity to witness this quiet, beautiful demonstration of the universe's elegant patterns. Until next time, clear skies and peaceful nights from Nebula Nights.